When designing an IIR filter, most designers choose a standard prototype, such as Butterworth or Chebyshev, and then focus on the filter's magnitude response specification. However, very few actually pay much attention to optimizing the time domain performance. As such, when looking at the step response and seeing overshoots and ringing, it's easy to think that this behavior can't be improved. A customer of ours working on turbidity monitoring in the food and drinks industry came to us with this exact challenge. Namely, is there a way of improving my IIR filter's time domain performance? Well, there is actually a relatively simple trick that you can undertake to achieve this, using the ASN Filter Designer's Pole Zero chart editor, which I'd like to share with you. Let's start by designing a low-pass Butterworth IIR filter. Now, let's excite this filter with a step input so we can analyze its time domain behavior. Opening the signal analyzer and selecting step response, we see that the step input causes the filter to overshoot and ring, which is undesirable. So, big question is, where does this ringing actually come from? Well, the answer lies in the pole positions. Returning to the pole zero chart and zooming in, notice that there are some pole pairs close to the unit circle. These make the filter behave like an underdamped system, which is why the step response shows oscillations before settling. So, how can we improve this? The simple answer is adjust the pole positions. But how? Well, by nudging the pole pairs that are close to the unit circle slightly inwards, we can increase the damping. But first we need to ensure that the passband gain remains at 0 dB when we're performing the nudging operation. Zooming into the passband and moving the data cursor over the middle region, we can enable the lock filter gain option, like so. Notice that a padlock now appears, and the tool will now automatically compensate for the changes, ensuring that the filter's gain remains at 0 dB at the position of the padlock. Returning to the pole zero chart and clicking on the pole pairs closest to the unit circle, we can interactively drag the poles and see the results in real time. Notice that as the poles move inwards, the step response immediately improves. That is, the overshoot is reduced and the filter settles much more smoothly. Although this adjustment does alter the magnitude response slightly, it improves the passband phase response, which in turn flattens the group delay, making the phase almost linear without the need of adding an all-pass equalization filter cascade. This not only reduces the ringing in the step response, but also helps maintain the harmonic relationships in the passband, which is why the waveform shape is much better preserved. And more importantly, we still maintain sharp stopband attenuation, ensuring that this is still a decent low-pass filter. And best of all, this optimization comes at no extra computational cost. That is, the filter order and structure remain exactly the same, and as such we can say it's an enhanced IIR filter, optimized for both time and frequency domain performance. Well, I hope that these tips have given you some inspiration to how small adjustments to the pole positions can make a big difference to your IIR filter time domain behavior for your IoT projects. A link for the ASN Filter Designer is in the description, so you can try it for yourself. Cheers, and I'll see you next time.